Hello everyone. Today's topic is sequential circuit flip-flops. Now in the previous lecture we have talked about the latches and we have got the brief overview of the working principle of the latches, which are basically unclocked flip-flop otherwise. Now in the latches described earlier, the output can change state at any time. The input conditions are changed. So they are called asynchronous latches. This operation of the basic latch can be modified by providing an additional control input that determines when the state of the circuit is to be changed. The latch with the additional control input is called the flip-flop. The additional control input is either the clock or enable input. Since this type of flip-flop responds to the changes in inputs only, as long as the clock is high, this type of flip-flops are also called level triggered flip-flops. Now triggering we will be discussing next. Now flip-flops basically are classified into SR flip-flop, D flip-flop, JK flip-flop, T flip-flop, and master slave flip-flop. Flip-flops are basically synchronous bistable devices. That is, they always have two stable. They operate in two stable states, 0 and 1. The term synchronous means that the changes in the output occur at a specific point on a triggering input called clock. Now let us talk about SR flip-flop. So as you can see here, in case of SR flip-flop, this is the logical diagram of a clocked SR flip-flop. So as you can see here, okay, and there is a clock over here, okay. So depending on this clock, the output will change. So there is a control over here. Okay. So this is a logic diagram of a clocked SR flip-flop using NAND gates. Okay. So as you can see here, there is a NAND latch, and with this configuration is that there are two NAND gates here. A common among them is a clock. There will be one input S and another input R. So set and reset. Okay. And there will be two output, where one output will be complementary of another output. So this is the typical setup of a SR flip-flop using NAND gates. So as you can see here, this is the block diagram representation of a clocked SR flip-flop. As you can see here, this is a clock. This is the representation of a clock. This block is a representation of a flip-flop. There are two input S and R and two output Q and Q bar. Okay. One thing it will be discussed, but still right now I will be telling here, if you can keep this in mind. So as you can see here in this clock, there is no bubble over here. Okay. There is nothing over here, isn't it? Simply a V-shaped is this one. So this is the representation of a positive edge triggering. Okay. Triggering we will be discussing in length in the next lectures. If a bubble will be there, then you should be able to understand that this flip-flop activates itself at the trailing edge of the clock, or rather negative edge triggered clock. As you can see here, this is the clock. Now as I told you, this is the positive edge triggering flip-flop. So with every positive edge, so if this is the clock, so for every clock, this positive edge, so when it will go from 0 to 1, okay, so this moment it will activate. Okay, so you can see here, whenever there is 1, there is a state change. When there is 0, there is nothing. So as you can see here, let us assume that it is activated. That means circuit is activated at the positive edge of the clock. Okay, now let us see the combination SR. When S and R is 0 and 0, we will get next state as no change, Qn. So Qn plus 1 is equal to Qn. That means there will be no change. when it will be 0, 1, that means this is a reset condition. You can see here, whatever may be Q, you will get output as 0. Whereas when it is 1, 0, that is the flip-flop will be then set to 1. Okay. But the problem is that whenever there is 1, 1, now it goes into invalid state. Okay. Why? Because both Q and Q bar obtains the same value, which basically violate our basic assumption when we started the flip-flop, that one output will be complementary, as you can see here, of another output, and thereby it is considered to be an invalid or forbidden state. Okay, and if it is 0, you don't care actually. So this is the truth table of a SR flip-flop. Now let us try to analyze the output of the SR flip-flop with the help of a timing diagram. Now we know timing diagram means what? Timing diagram means the response of the flip-flop with every clock. So as you can see here, suppose I gave S input like this. Okay, so it was 0, then it goes to 1, and for this finite time interval it is 1, then again it goes back to 0 and it remains 1. So this is my input S, and suppose this is another input R. So this will be till here it is 0, but suddenly here we give 1 up to this one, and again it goes to 0. So this is the given input. Okay, and suppose this is the clock. Okay, and this is the clock. Okay, so what will happen when a clock is there and we have the two input S and R like this? So how will be the output behaving? You can see here, this is how the output will excuse me, this is how the output will behave. Okay, how? From where we are getting this? Okay, so in timing diagram, as you can see here, suppose S is here, S is how much here? S is 0, R is how much? 0. Okay, what is here? Clock is not activated, so nothing will happen. Okay, whenever there is 1, you can see here positive is triggering. Whenever there is 1, it will see this one. Okay, how much is here? 0. How much is here? R 0, 0, 0, no change. That means you see whatever was Q, it was following the same output. Okay, follow the same output till again the positive is triggering. What it gets over here? It gets S1 and R0, set condition. See, suddenly it goes to 1. Okay, it will remain till next positive is triggering. You can see here. Suddenly it finds that the circuit is basically the SR flip-flop activates over here at this point because there is a positive is triggering, and it sees that here S is 0 and R is 1. It's a reset condition, so definitely here it goes back to 0, and again it returns to 1 till this point, and here again the positive is triggering happens, and it sees output as S1 and R0. So it will set itself. Okay, and as you can see here, S is 1 and R is equal to 0 for the entire duration over here. Okay, so it will retain this 1 throughout. So this is how we basically try to visualize the working principle of the flip-flop output with the help of timing diagram. That means with each clock. Now let us go to D flip-flop. Okay, so D flip-flop. So what does it D mean? D means delay. Okay, D means delay flip-flops. As you can see here, this is the logic diagram of a clocked D flip-flop. It is a simple logic diagram. This is the logic diagram of SR flip-flop. In this S, we put input D, and the another input we put one inverter over here. Okay, so when we use this inverter, what will happen? This 1-1 condition will be avoided. How? Suppose D is 1, so S is 1, and as there is inverter, R is 0, so it will be 1-0 condition. So S1 R0. But if D is 0, what will happen? Here will be 0 and here will be 1. That means reset. So either the output will set or the output will reset. These are the two states which it can go. for the D flip-flop. But okay, I will tell you first. Have a look and circuit. As you can see here, simple SR flip-flop configuration. Just in place of S, I connected one D and another end. I put one inverter and put it in the R input. Clock is common for both. Okay. So the thing which I was telling you. So this is the logic diagram of clock D flip-flop using NAND gate. So the thing which I was telling you, that which is very interesting actually, that when D is 1 means what? S is 1 and R is 0. So S is 1 means what? Whatever may be Q, it will set 1. On the other hand, when D is 0, what has happened? S will 0 and R is 1. Okay. So R is 1 means what? Whatever may be in the Q, it will reset to 0. That means you can also visualize this like this. If I give D here 1, here will be 1. If I give D over here, here will be. If I give 0 over here, here will get 0. Whatever may be the previous input, previous output. So that means what? We are getting the same input across the output. Okay. So what is the advantage? Delay. The advantage is the delay. So using this configuration, we can introduce the timing delay. Okay. And this timing delay will be simply equal to the propagation delay. Okay. So if you give input here, okay, and after after this delay, that means when you give input and you get output, it goes through all the gates over here. Okay. It goes through all the gates over here. Every gate from input to output, there is a delay. So upon this whole delay, you will get one thing which is called propagation delay. Okay. So this delay or the timing of the delay will be equal to the propagation delay of this circuit, and therefore this type of flip-flop is called D flip-flop. As you can see over here. So this is the block diagram of a clock D flip-flop. Obviously it is positive as triggered. You can see here it is having only one input D. Now I explained everything. So suppose if it is positive as triggered, D is 0. You can see here Qn plus 1 next state is 0. When D is 1, next state is 1, irrespective of what was Qn before. Okay. When clock is 0, you do not have to consider anything because it will not activate itself. So we discussed the truth table of a D flip-flop. Okay. As I told you that there will be no forbidden state in this flip-flop. So it will simply avoid this, that 1-1 condition of SR flip-flop, and this circuit will not go into forbidden state or invalid state. Now let's talk about the characteristic table of D flip-flop. As you can see here, this is the characteristic table of D flip-flop. So as you can see here, how to write characteristic table is also the thing. You can see here, first of all, you have to put here input D, then present state Qn. You have to take all the combination of the present state, and the next state is Qn plus 1. So when D is 0, and suppose Qn or the present state is 0, what you will get? Simply you will get 0. When D is 0, and whatever, and even the present state is 1, as it is 0, it will follow the output, and there will be 0 only. But suppose D is 1, and the present state is 0, the Qn plus 1 or the next state will be 1. It will simply follow the input. You can see here, it will simply follow the input. Okay. So if here it is 0, if here you are giving 0 volt, here you are getting 0 volt. If you are giving 5 volt, definitely 5 volt will occur across the output. So simply the output will follow the input. The only thing which is signified over here is the delay factor, which is equal to the propagation delay of all the flip-flop, and that is the significance of delay flip-flop or D flip-flop. Now let us talk about the Jack KB flip-flop or JK flip-flops. It is also a storage element, very interesting one. So as you can see here, this is a logic diagram of a clocked JK flip-flop, okay, where there are two inputs J and K. Okay, but you can see here there is one very interesting connection over here. Another input is gone to the Q bar, and here for this K1 it goes to Q. Okay, so this is the change or the modification which has been done to the SR flip-flop. Now what we will get eventually? Okay, you can see here, this is by using NAND gate. As you can see here, JK QQ bar. So this is the block diagram of a clock JK flip-flop, and this is the truth table of positive edge triggered JK flip-flop. Now let us see for the positive edge triggering. Let us assume for the from beginning to end that we are using the positive edge clock. So there should not be any matter whatsoever. Okay. So when JK is 0 0, okay, even it is a negative edge triggering, there will be no problem because our circuit will activate at the either the positive edge triggering or the negative edge triggering. Depends on the clock, but we have to take the transitions accordingly. So when JK is 0, it will simply, see here, JK flip-flop will behave exactly as the SR flip-flop, but the problem, or rather the violation of the 1-1 condition, that means S is equal to 1 and R is equal to 1, which we were getting in the truth table, will now be addressed using JK flip-flop. So other things remain same. Okay, and you can see here, when SR, suppose you think that this is S, this is R. So when 0 0, we know that there was no change. Here also you can see there is no change. 0 1, you can see it's reset. You can see here circuit is resetting. Where it is 1, you can see here 1 0, it will set. But 1-1 condition which was basically forbidden in SR flip-flop, now it will enter into toggle state. Now this is called toggling. What do you mean by toggling? Toggling means, suppose JK is 1 1. Okay. Suppose J is 1 and K is 1. Okay. And suppose Q is 0 and 1 over here. Let us say it is 0 over here. We will not consider this because anyhow it will be the complementary of Q. So suppose if there is 0, okay, if there is 0 over here. So when this is 1 1, when there is 1 1, so for one clock it will be 1 because it will be, you can see here Q and bar. So whatever is 0 over here, with the first clock it will go to complementary, it will become 1 from 0 to 1. Okay, from 0 to 1. Okay, in the next clock what will happen, it will again convert from 1 to 0. So 0 1 0 1 0 1 0 1, so it will toggle. Okay, it is toggle, and this condition is called toggling. It is a disturbance. Okay, it is a disturbance, and we should be able to solve this problem, and the answer we will be getting is a master slave flip-flop. Okay. As you can see here, toggling should be eliminated completely, and the configuration which we will be using to eliminate this toggle is called master slave flip-flop configuration, which we will be discussing next slides. But before that, let us go to the characteristic table of JK flip-flop. Okay, as you can see here, JK, there are two inputs. Okay, and this is the present state. So we will take all the combinations and we will see the next state or the next output. Okay, so when JK is 0 0, we know that whatever there was in Q, we will get across it. Whatever there was there in the present state, we will obtain at the next state. Okay, okay. So 0 0, there will be no change. So that means whatever is there in the present state, in the next state, that is after excitation, it will remain same. 0 1 is a reset condition. That means whatever will be in the next state, it will be reset to 0. 1 0 is a set condition. That means whatever is there in the present state in Q, the next state will be set. The 1 1 condition is a toggling condition. That means if the present state is 0, the next state, that means after excitation, it will be 1, and if the present state is 1, after excitation it will be 0. So likewise you have to make the characteristic table of all the flip-flops. So timing diagram, as you can see here, if this is J and if this is K, okay, and if this is the clock, So as you can see here, this is the Q. Okay. So as you can see here, this positive edge of the clock. Here we see J is 0 and K is 1. That means reset. You can see here it is coming back to 0 because it has started from 1. At this, it will retain it till the next positive edge, which is here across C. It will look for inputs at this point. It will see J as 1 and K is 1. So that means it is a toggling condition. That means whatever was there and what was there, it was 0 here. So it will toggle, it will go back to 1. Again at this point E, there's a positive edge and it will look for inputs and it finds that K is 0 over here and J is 0 over here. That means no change. J 0, K 0, no change. That means see, it is coming back here. Here also, it will look for inputs and it is looking that K is 0 over here and S is 1. Okay. So 1 and 0 means 1. So it was already 1. So it will retain it. Again, it will come here and it will look for input. And here it will see that K is 1 and J is also 1. Same. It is a toggling condition. 1, 1. So what will be there at the what will be in present state, which is 1 over here, it will be Q bar. That means it will come back to 0. And likewise, we have to prepare the diagram. This diagram is called timing diagram because it depends on the timing of the clock. So there will be inputs, whatever, 1 or 2. Here it is a JK flip-flop. That means there will be two inputs, J and K. And based on this clock, the output will change. Now race around condition. As you can see here, race around condition means what? So you can see here, for JK flip-flop, if J and K was 1 and if clock is equal to 1 for a long period of time, okay, what does it mean? It means that suppose this is the clock, okay, and this clock has time delay T, okay, this clock has time delay T, okay, and we have talked about the propagation delay of the flip-flop. That means the delay when input is given and output is taken. Suppose if this time delay of a clock is more than the propagation delay of the flip-flop, what will happen? It will happen that this output will basically go on changing. So if it is if it is suppose J1 K1, that means it is a toggling condition, isn't it? So suppose if this is Q, okay, so suppose at this point, okay, at this point it goes back to 1, but even if it goes back to 1, okay, the clock is still active, so it will go on and on, isn't it? Because for this whole clock, suppose it is T, and if this is, I mean, if the flip-flop is TP, when T is greater than TP, the circuit will still be active and it will go on from 1 0 0 0 1 0 1 0 1 and so on. And this becomes uncertain that at this, when the clock will be finishing, we don't know what will be here. Okay, and that's the uncertainty. Okay, so as you can see here, for JK flip-flop, if J is equal to K is equal to 1, and if clock is equal to 1 for a long period of time, then Q will toggle as long as clock is high, which we talked just now, which makes the output of the flip-flop unstable or uncertain. This problem, you can see, this problem is called race around condition in JK flip-flop. Okay, how it will be avoided? The problem race around condition can be avoided by ensuring that the clock input is at logic 1 only for a very short time. Okay, so suppose here, so it should be maximum over here. Okay, so T should be less than TP. Okay, this problem is solved by introducing the concept of master slave JK flip-flop, which I told you just now, that in JK flip-flop for one condition there will be toggling. But if the clock, because the excitation will be happen for each clock, but if a clock has a time duration T which is very greater than TP, that is the propagation delay of the flip-flop, what will happen is that the toggling will go on and on and on. And when the clock will end, eventually we don't know what will be the state. Okay, this problem, which is called race around condition, will be solved using JK flip-flop, master slave JK flip-flop. Okay, which we are going to discuss just now. But But before that, let's go to one of the interesting flip-flop, and that is a T flip-flop. Specifically, on purpose, we use various flip-flop. Okay. So as you can see here, this is a block diagram of clock T flip-flop. Okay. Now, regarding this T flip-flop, I just want to tell you that T means nothing but toggling. Okay. So we want this flip-flop to have only one state, and that is toggling. It should toggle. That is the purpose of this flip-flop. It should toggle. Okay. And how we are going to do that? It's very simple. So suppose if this is a JK flip-flop, short this J and K and take one input T. Okay. So if we give, okay, we will discuss over here, characteristic table. Yeah. You can see here, when T is 0, okay, so that means if this is JK flip-flop and if T is 0, so common input is T over here. So that means if here is 0 and as these two are shorted, okay, that means here will be 0 and here will be 0. That means J will be 0 and K will be 0. J0, K0 is nothing but no change condition, isn't it? So whatever will be there in Q, there will be no change for 0 over here. But whenever there is a 1 over here, here it will go 1 and here it will go 1. JK1 is toggling. So whatever will be there in Q, next state will be Q bar. And the same is reflected over here too, as you can see here. So if this is 0 and if present state is 0, next state will also be 0 because of no change. And when there is 0 and if the present state is 1, next state will become 1. And when there is 1 over here, so you can see here, it will toggle. So 0 will be 1 and 1 is 0. So this flip-flop, the purpose of this flip-flop is that this flip-flop should toggle always. It is purposely used for various counter operations, which we will be discussing in the coming lectures. Now let us talk about the master slave flip-flop. As you can see here, the configuration. Okay. Now we have divided this clock into two. Okay. So you can see here, there will be two JK flip-flop. Okay. There will be two JK flip-flop. One JK flip-flop will be serving as a master, another JK flip-flop will be serving as a slave. Okay. And clock, you can see here, this clock is connected with the help of an inverter with another clock. Okay. So this is the block diagram of a clock master slave flip-flop. Okay. So what will happen? The master is set according to JK while the clock is high. Okay. The contents of the master are then shifted into the slave when the clock goes low. This particular flip-flop might be referred to as pulse triggered to distinguish it from the edge triggered flip-flop. Now what does it mean? Okay. You see here, suppose, let us discuss this. Suppose here is, suppose this is the positive, it's not suppose, it is a positive edge triggered. So when there will be 1 over here, okay, JK will be excited and you will get something here, depending on what you put here, J and K. So you will get here output, isn't it? You will get here output. Okay. And suppose this is 1. So till it is positive, so till it is from 0 to 1. Okay. From 0 to 1, and that is positive edge triggering. So when the clock goes from 0 to 1, okay, it will be activated. And you will get here the output. Okay. But as soon as it goes from 0 to 1 to 0, now what will happen? As there will be a 0 over here, okay. So now this will be active. This will be activated. This will be activated. Okay. And if this will be activated, you can see here, it will find that here was something depending on this JK flip-flop. Okay. Let us assume that there was 1 and 0. So that means it is set. Now suppose whatever will be there, it will be 1 over here. Okay. So at the negative edge of the clock, what will happen is that it will find here 1 and here will be 0. So it will simply, there will be 1 over here only. So it is just carrying this output at this output. Okay. So therefore it is known as, it is actually referred to as pulse triggered. Why? Because now you can see here it's behaving as if at the positive pulse this is activated and at the negative pulse this is activated. Okay. this slave which is referred to will simply copy the output of the master flip-flop and it will put it here. Okay, and because of this, for this whole clock, so from 0 to 1 it will be output across here, there will be no change, and from 1 to 0 this will be activated and will simply copy the output and it will give the output over here. So there is no possibility of reaching the race around condition in case of master slave flip-flop, which is a clear advantage over the JK flip-flop. The timing diagram, same, let there be a clock like this, and if this is J, and you can see here the K. Now you can see here master slave flip-flop will very clearly obey whatever the instruction will be given, and the slave will just copy the instruction at the trailing end. As you can see here at the positive end, as you can see here at the positive end, as you can see here, J is 1. Suppose this is positive edge. J is 1, K is 1. Okay, when J is 1, J is 1 and K is 0. So 1 0 means set. So as you can see here, it is going high. Till what time it will go high? Till this time. Okay, till this time. Why? Because it is trailing edge. Okay, so there is a possibility of changing the clock. Okay, but what happens at this trailing edge? The slave will activate itself. Okay, and it will simply copy the instruction. If there is 1, here it will output as 1. So likewise, we can avoid the race around condition in MS flip-flop. Thank you.